This is 7.2, division properties of exponents. Our last note section was in regards to multiplying exponents. Now we're going to talk about dividing. So you're going to see a lot of similarities or just inverse operations going on. The quotient of powers rule. Quotient implies division. So what happens when you divide powers? So if I have an x to the fifth on top and I am dividing by x squared on the bottom, there's a quotient of powers. When I expand that, I will get 5x's multiplied on top, repeat multiplication, over 2x's on the bottom. And just like any other number, anytime you have a number over itself, it simplifies to 1. When you have a 3 over a 3 or a -2 over -2, they simplify to 1. I don't want to say that they cancel. They reduce to 1. And so this x over x becomes a 1. This x over x becomes 1. So we have a 1 times x times x times x, which becomes 1x cubed, or we can just call that x cubed. So when we divided x to the fifth by an x squared, we were left with x cubed. How do I get a 3 out of 5 and a 2? Is subtraction. And so that writes our rule. When you have some common base, a, to some power, and you're dividing by that same base, a, to some other power, you subtract the exponents. And so what you end up with is a to the m minus nth, and you have your subtraction. Okay, as an example, if I have t to the 7th over t to the 3rd, rather than expanding it out, I can subtract the top from the bottom. You have to do top minus bottom, and you end up with t to the 4th. And that's it. You know, division is the opposite of multiplication. When we multiplied powers, we would add the exponents. So it seems only fitting that when you divide them, you're going to subtract the exponents. The next rule involves taking a power of a quotient. So I'm going to have a x over y. This is a quotient, but then I'm raising that to some power. In expanded form, what that tells me is I'm multiplying an xy times another xy, and that's an x times an x over a y times a y, which becomes x squared over y squared. Now, if you look at that, really, to save myself all that work of expansion of saying an xy times an xy and then expanding it out, you really, the rule is you just apply the power to the numerator and the power to the denominator. So if you have some quotient a over b raised to some power, you're going to apply the power to the numerator, power to the denominator. And to show you an example, if I have x cubed over y squared, and I'm going to square that, I apply the power to the numerator, which is a power to a power, so I'd multiply from yesterday, x to the 6th, and then the squared y to the 4th, you multiply. X to the 6th over y to the 4th. Zero exponent. Let's expand a zero exponent. I'll kind of show you how you could get 0. So it involves when you have a number on top, x to the 3rd, over its same amount, x to the 3rd. If I use the rule from above and subtract, I could expand it too. But so let's expand, and I get x times x times x over x times x times x. Well, what's going to happen here is that all 3 of them are going to simplify to a 1, and so you end up getting 1. You have a number divided by itself. The reason I put this here is if you look at this, and let's just go down into the blank space and use our quotient of powers rule that says if you have x to the 3rd and you're dividing by another x to the 3rd, we could subtract the exponents and you end up getting x to the 0 power. So when I use the rule, I get x to the 0. When I use expansion, I get 1, which means I did the same problem differently. It looks like I got different answers. I did get in different answers, but it defines what a 0 exponent is. And that's our rule for a 0 exponent. 0 exponents simplify to 1. So any number raised to the 0 power is 1. You have to be careful what's being applied to the 0 power. So in the example, if I have this entire x squared y cubed, that whole quantity raised to the 0 power, it just turns into 1. I don't have to show any work. It's something that we memorize. Okay, I showed my work in the expansion, so you don't have to show your work later on. For negative exponents, I want to do the same thing. I want to show you the work with the expansion, show you the work with the rule, and show you how they equal. Okay, that comes up with our definition. So for negative exponents, I'm going to show you an expansion that where the number on top is smaller than the number on the bottom. And so when I expand x squared divided by x to the 5th, I end up getting 2 x's on top and 5 on the bottom being multiplied together. And when I simplify and they become 1s, it's really important to say that they become 1s because there's a 1 left over on top. So this simplifies to 1 over x to the 3rd. So that's my answer when I actually expand it out. When I use my rule, come down in the corner here, if I use my rule, x squared over x to the 5th, I will get a negative exponent. When I subtract a 2, take away 5, it's always top minus bottom, you will end up with x to the negative 3rd. So my rule gives me a negative exponent. My expansion gives me a reciprocal, which leads us into the definition of negative exponents. If you have some number, a, raised to the negative mth power, you are not allowed to leave it as a negative. You must simplify that. And how you simplify that is you take the reciprocal and it changes the m to a positive. You flip it. And vice versa, if you had 1 over a and the negative was in the denominator, you flip it and it becomes a positive and it becomes a whole number. So it becomes a whole number with a positive m. So negative exponents you flip. Okay, you only flip which has a negative. So I'm going to show you a pretty complex problem to kind of understand that. So let's make a to the negative 3rd. Let's make b to the positive 2. And then let's put them over c to the negative 4th. Okay, so the only things that will flip are the things that are negative. So a to the negative 3rd is negative, so we're going to bring it down to the denominator and make it positive. B squared is not doing anything, it's positive, so it stays on top. And c to the negative 4 is negative, so to make it positive, we have to flip it up top. So b squared stayed, the a went down below to become positive, and the c went up top to become positive. All right, so let's go ahead and try some problems. Again, you're going to do both expansion and the rule to help until you understand this. And then on the quiz, I don't care what you use. All right, so we got a to the 5th, b squared over ab cubed. So expansion tells me I have 5 a's on top. I have 2 b's on top. I have an a on the bottom with 3 b's. Using expansion, one set of a's turns into 1. 2 sets of b's turn into 1s, and so I am left with 4 a's and 1 b in the bottom. So let's see if I can make that same thing happen using my rule. Using the rules, I'm going to subtract. I'm dividing, so I'm going to subtract the exponents. When I subtract my exponents, the a in the denominator has an exponent of 1, so it's going to be a to the 5 minus 1 is 4. And when I subtract my exponents with the b's, I have b 2 minus 3 is negative 1. So I have a to the 4th, b to the negative 1. Just to reiterate, you must subtract top from bottom, and then it always is a numerator when you do subtraction. But I can't leave my answer this way because it has a negative exponent, and you're not allowed to keep it as a negative exponent. So the last thing I'd have to do is flip the b to make it a positive 1. You can write it, and you don't have to. So our answers match. Number 2. What I like about number 2 is it has numbers. Again, the numbers are going to throw you off because you're confused. These rules that we're writing are only with exponents. Numbers aren't exponents. So when I do my expanded form for number 2, I'm going to put the -2 with the -6. I'm going to write it as a fraction. Those are numbers. We simplify them the way we've always simplified numbers. And I'm going to just keep it separate. I'm going to put the k with the k, and then the 6 k's underneath that. So put the like things together. All right? So when I have a -2 divided by a -6, that's actually 1/3. Don't do any subtracting. They're just numbers. You're simplifying. My k's, 2 of them cancel, which leaves me a placeholder 1 in the top, and then I have 4 k's remaining. So I'll have a 1 over k to the 4th, which when I combine all that together, I have a 1/3 times a 1 over k to the 4th. It becomes 1 over 3 k to the 4th. So let's see if I can get that answer using the rules. So when I do my rules, numbers aren't going to change. The numbers are going to just divide like we've always divided. So -2 divided by -6 is going to give me a 1/3. I'm simplifying the fraction. And then k squared divided by k to the 6, I'm going to subtract the exponents. 2 minus 6 is -4. Can't leave my answer that way. So the k to the -4 has to come down below and become positive. So 1 over 3k to the 4th. And they match. All right. Number 3 here is a power of a quotient. So expansion, I'm going to write it twice. So since it's telling me to square that fraction, I'm going to write 2p over 3w to the 3rd times 2p over 3w to the 3rd. Another way to start that expansion is you got to have 2 2's, right? 2 p's over 2 3's and 2w cubes. That's another way of writing that expansion. And what I like about that way is you group the like things together. So to clean that up, I'm going to have 4p, I'm going to have a 4, sorry about that. I'm going to have the 4, and then if I look at my p's, it's not going to cross off with a w, so I do have to put them together. 4p squared, the 3 times 3 is going to make 9, and this w to the 3rd times w to the 3rd makes w to the 6th. Remember, when you multiply, you add the exponents. So I end up with 4p squared, 9w to the 6th. Using the rule, you just, in a sense, distribute that power to everybody inside. So I always like to give them all their powers. Okay? Anybody that doesn't have a power, I want to put a 1 with them. So that when I do a power to a power, it becomes 2 squared times p squared times 3 squared over w to the 6th. Everything got squared. And so the 2 squared becomes 4, p squared stays, 3 squared becomes 9, w to the 6th stays. Number 4, the only thing that is being taken to the 0 power is the m. So whether you're going to expand or not, that just becomes a 1. But the only thing that becomes a 1 is the m. And so expansion here would say n over n and n. They cancel. I am left with just an n. If I were to use the rule, I would still cross off or eliminate the m to become a 1. And I'd subtract 3 minus 2 is 1n. Okay? Now, if that 0 is applied to the whole thing, the whole answer would be 1. So you got to be careful with those 0 exponents. They're easy, but they're also easy to confuse where you apply it. Number 5, I have a whole number 7 raised to the -2nd power. Remember, every whole number is over 1. And so when I flip it, it becomes 1 over 7 squared. I flip it, the 1 goes on top, and then the squared becomes positive. And so that's 1 times 7 squared is 49. 149. Really no other way to do that. I guess I could show 7 times 7. Excuse me, number 6. All right, we got a 4. We got 3 C's. And I'm going to start with a line because I need to move these D's down below. So I have my 4, I have my 3 C's. Now my D's to the -2, I'm going to put down below. I have my 5 down below. And these c to the negative 4s in the bottom need to come up top. So there's 4 c's on the top. And then d to the 7th stays, so 7 of these d's. All right, sometimes it helps to start with the fraction bar, and then you have room to put everything else. Nothing is going to cancel, nothing's going to simplify, so I end up with 4/5, that's the number, and then I have a total of 7 c's on top, 7c to the 7th, and then on the bottom I have 9 total d's, d to the 9th. That's expansion. If you're going to use the rule, my suggestion was to get everything in positive sense first before you start applying the rule. Because things flip, if those c's go up top, maybe you're dividing in the beginning, but maybe now you're going to add. So there's more than one way to these problems. So I'll write the 4, I'll write the c to the 3rd because it's positive, but I'm going to bring that c to the 4th up and make it positive. My 5 stays down below. My d to the negative 2 goes down below and becomes positive 2. That's at d to the negative 2nd. And then d to the 7th stays on the bottom. So even though we're dividing, because the c's are now multiplying, I have to add their exponents. So 4c to the 7th over 5d to the 9th. Okay, so I showed you expansion. I showed you where I worked them into the positive and then I applied my rules. I want to show you if you just do straight up rules. I'm going to show you a third way on this example. Okay, the 4/5 just kind of stays there. But if I take this c cubed and subtract negative 4, that becomes c to the 3 minus negative 4. That's c to the 7th. Becomes plus 4. And if I take that d to the negative 2nd and subtract 7, I end up getting d to the negative 9. So I get 4/5 c to the 7th, d to the negative 9. And I can't leave my answer that way, so I just have to bring that down. 4c to the 7th, 5d to the 9th. I just showed you 3 different ways to do the same exact problem. Okay, my favorite is red. Maybe some of you say, I understand green better. Or maybe you just like to use the direct rule of subtraction and you can work it. Be careful of your signs. So all of them are right. Whichever one makes more sense to you is the better choice. All right, we are almost there. Number 7. For number 7, I got d to the negative 3rd. So that's actually going to become 1 over d cubed to the positive 3rd. D to the 0 just becomes a 1. And then d to the 6th. So I have 6 d's on top, 3 on the bottom. And when I expand that out, 3 of them simplify to 1. I am left with a d cubed. That's using expansion. If I'm going to use the rule, I still realize that I had to flip my d to the 3rd, or I could just simply say, well, I'm multiplying. So d to the negative 3rd times d to the 6th. I add these exponents, and I get d to the positive 3rd. I don't have to worry about flipping. I just use a different rule. That's the multiplication property. D to the 0 still turned into 1 in each case. All right, I'm going to skip number 8. And let's go on to the last example. The area of a triangle, find the length of the rectangle. I think that's a mistake. Let's go back to 8. I have no idea why. Oh, I'm sorry. I think it's just triangle supposed to say rectangle. So the area of a rectangle. Okay, that's the area of this thing. And then they want us to find the length. So they give us the width. They want us to find the length. The area of this thing is 32, x to the 4th, y to the 6th. So if you remember, area is equal to length times width. Substitute the value of the area, 32, x to the 4th, y to the 6th, is equal to, we don't know the length, but we know the width, 8x cubed y squared times the length. Okay, since it's multiplication and we're trying to find the length, we're going to divide both sides by this amount. And so the length will equal whatever this quotient is. So 32 divided by 8 is 4. Okay, and I have x to the fourth over x cubed is x. And then y to the sixth over y squared is y to the fourth. Okay, and then I could actually expand that out one last time. The 32 over 8 is going to be 4 no matter what. I have 4 x's on top, 6 y's on top, and then I have 3 x's on the bottom, 2 y's on the bottom. The 2 y's cancel. 3 of the 4 x's cancel. And so what you're left with is a 4x with y to the fourth. There's 4 y's left over, there's an x, and there's a 4. Okay? So I showed you, I know they're long, but we had the rules and the expansion. I'd like to show you both because if you get stuck, rather than guessing and guessing wrongly, or if you get the wrong answer, I'm going to have you fix it using expansion. So write something that you need clarification on, and then here's your problem. I want you to simplify. I want you to try to use the rule and then check it with expansion. So I should see both forms on your homework. Good luck.